Okay. Jean-Philippe, second
Yes.
part, please.
Okay. Okay, good. So the second part is really along the same line, trying to understand these anomalous fluctuations, these excess fluctuations in financial markets and economies at large. And so the title is, Will a Large Economy Be Stable? And the need for out of equilibrium economics. And of course, the title is inspired by Robert May's celebrated 1972 paper, Will a Large Complex System Be Stable? So, okay, this will sound a little similar to the previous introduction, although it's maybe a little more precise. So if you look at the US GDP growth since the 50s, goes up and down quite a bit, maybe less in the more recent period. Of course, this stops in 2020. But still, overall, the fluctuations are very large in the sense that the GDP growth is on average 3% per year since the 50s, but with fluctuations that are of the same order of magnitude, so plus or minus 2.5% a year. And this is, again, hard to explain from standard economics thinking. And so the fact that these fluctuations are large was called the small shocks large business cycle puzzle by Ben Bernanke. Ben Bernanke was, of course, the head of the Fed for many years. Business cycle in economics lingo means just the fluctuations, year-on-year fluctuations. So you see that this large amplitude is the large business cycle, and the small shocks refers to the fact that there was no obvious reason for these large swings in growth rates. And so, again, there's a question of exogenous versus endogenous fluctuation. If exogenous fluctuations cannot explain what's going on, maybe we should think more deeply about endogenous fluctuations. Of course, again, this is not to say that there are no exogenous fluctuations. COVID is one good example, but as I've explained in the previous talk, the subprime is much more difficult to really account for. The standard DSG models, the standard dynamic stochastic general equilibrium models of economists, is ill-equipped to deal with endogenous crisis. Actually, again, the idea of these models is to say that the economy is fundamentally stable. It should reach equilibrium fast, quote unquote, and this is something I'm going to speak about a lot further on. And then the whole system is shocked externally by COVID, by technology disruptions, and so on, and this leads to fluctuations. But absent these shocks, it's very hard to understand why there are so much fluctuations. And it's really the same story in financial markets. If you look at any standard well-traded stock, it goes up and down 2% per day, which in itself is huge. Why would the value of a company goes down, up or down 2% every day? I mean, it doesn't seem to make sense. And actually, if you calibrate models that are trying to capture feedback of activity on itself, you find that 80% or 90% of this volatility seems to be of endogenous origin. So really, it's important to understand these aspects. And here I want to quote two economists. One, John Cochrane, in 1994, wrote, "What shocks are responsible for economic fluctuations? Despite at least 200 years in which economists have observed fluctuations in economic activity, we are still not sure." So this was 1994, but I think that for most classical economists, it's still the same question. And then Jean-Claude Trichet was at the helm of the European Central Bank in 2010, after the 2008 crisis, said DSG, that is these classical models, DSG models failed to predict the crisis and seemed incapable of explaining what was happening. In the face of the crisis, we felt abandoned by conventional tools. Okay, so what are the hypotheses that have been put forth to explain these large, the amplitude of GDP growth in large economies, with in mind, and I'll try to give you a better argument than just hand waving from models that economists use later on. But in a nutshell, the argument would be that if I have n independent firms that do their business, each of them has fluctuations of any sort, but idiosyncratic fluctuations. And by the central limit theorem, this should average out and give the economy the overall volatility of the economy going down as 1 over square root of n. And so if there are, I don't know, 1 million farms in the US, this should lead to very small numbers, much smaller than the ones that we observe. So what's the catch here? Well, some say, okay, we don't observe shocks, but they exist and they're hidden to the economist, but people know. The almighty market knows. I don't know how, but that's one kind of argument that you see written down, is that somehow economists are blind to these macroeconomic shocks, but they exist, and people who are informed know about them, and this is the reason why the economy is fluctuating. I think I really hate this interpretation, because it means that there cannot be any science then. I mean, if you invoke unknown causes to explain effects, then better do another job. The second serious proposal is due to Xavier Gabex, who says, well, if you look at the distribution of firm sizes, it has a fat tail, a parallel tail. I'll show you data later on. And as we know, if distributions have fat tails, the central limit theorem doesn't hold. And it doesn't hold because the sum is dominated by a few large terms in the sum due to the fat tail. And so this means that there are large firms in an economy, and maybe their fluctuations dominates the fluctuations at the level of the whole economy. So this is certainly true, that distribution of firm sizes is fat-tailed. There are various problems with this interpretation. One of them is that we still don't get the right order of magnitude. And the second is related to the next point, which is that in this interpretation, it's really the ailing of one firm or a few firms that dominates these fluctuations, whereas actually we see that the economic activity goes in sync between different firms. So there's this idea that there's network effects, contagion, bankruptcy waves, bank defaults, and so on, that must be relevant in the way we escape the central limit theorem. That is, it's not because of large firms, it's really because of large correlation between firms that we escape the 1 over square root of n. There's another line of thought that's been initiated by Per Bak, and in particular in the paper with two classical economists, I mean fringe but classical, José Schenkman and Woodford in 1993, where they proposed that maybe the large fluctuation that we see is due to the fact that the system is close to a critical point, and so that there's a kind of self-organizing mechanism driving the system close to a critical point, and because of the proximity to a critical point, you get enhanced fluctuations. And so I've discussed this in a review paper last year, if you're interested. And then the last scenario that one could consider, and that I'm going to motivate later on, is the fact that we should forget about equilibrium in economics and think of out of equilibrium phenomena, that actually the dynamics of economic systems is very complicated and doesn't allow the equilibrium to be reached. And so that we're in a kind of turbulent state, which is always out of equilibrium. So all the estimates of volatility based on equilibrium arguments are really off the mark. So in order to motivate this discussion, let me give you an idea, a glimpse into the classical model of firm networks that economists work with. So this is a graphical representation of the input-output network in the US. So the three red squares correspond to three automobile industries, and so you see the relation between suppliers and customers in this firm network. And so just graphically, it's clear that there must be some contagion effects in these economies. Okay, so the classical model is the so-called Long-Plosser model that was invented in the 80s, but it was revived recently by Acemoglu, who got the Nobel Prize in Economics, for those who don't know, this year, Carvalho and collaborators in 2011. And this paper has really been cited many, many times and has already a lot of follow-ups that I will quickly mention. So this model starts with the idea that there's a representative household. As I said, the whole household sector is condensed into one representative guy or girl who's going to buy goods, final goods. But there are n firms that are different and that produce different things. And so firm I produces using labor. The labor comes from households, of course, but it also needs other goods to produce. And in order to know how much firm I is able to produce, you have to invoke what's called a production function. And the standard production function that is used is called the Cobb-Douglas production function. And don't ask me why it's written that way, because I struggle to understand the logic of writing a production function this way. But it is the workhorse of many of these papers. So I'll guide you through the production function and then give you alternatives to other production functions. So what is this? This yi is the output of firm I, knowing its input. So labor is the number of hours worked by employees to some power, and then the product over input goods to firm I. So this is product over J of the suppliers of I, belonging to the suppliers of I, of the amount of goods J bought by firm I to some other power, alpha Jij. So the Jij is a matrix capturing the structure of this input-output networks, which is normalized in such a way that this production function is scale invariant. That is, if you multiply all Q's by lambda and L by lambda, then Y is multiplied by lambda. So this means constant return to scale, which might not be the case, but let's focus on this example first. And then there's a Zi in front of all this, which is called the productivity factor. And this will capture the shocks, because the idea is that when there's a change of technology, then with the same amount of goods and labor, you're able to produce more and or less. And so all the fluctuations will come from this little guy Zi here. Okay, so this is a kind of chemical formula, if you want. I mean, this of course, chemical formulas are all about rates, but let's assume that this is true, that yi is the product of labor to some power and q to some other powers. Then you turn the crank, and so economic equilibrium means that households maximize their utility from consumption. I've talked about utility earlier on in the previous lecture. And so this is going to give a consumption of good I by the household sector, which is essentially inversely proportional to the price of that good. Firms, on the other hand, they maximize profits. So what is the profit of firm I? Curly PI is a profit. It's the amount of goods that it sells, that it produces, times the price. But already we're going to make the assumption that I'm going to speak about in a second, which is that that market's clear. That is, everything that's produced gets consumed. So this is a very strong assumption of economic equilibrium, but it's the standard one. So instead of writing here the sales, you write the production, because you assume that markets will clear And so everything that's produced gets sold. So this is the income, YIPI. Then it spends some wages on labor, and then it spends some money on buying input goods. So this is the sum over input goods, so suppliers of I, of the amount of good J bought by I times the price of good J. And then the last thing you need to close the system and have enough equations to determine everything up to a scale factor is that markets clear, that is all the possible labor is employed, and all the production of YI is either bought by the household sector or by other firms. So you see sum of a J of QJI now is the amount of good I bought by J summed over J that has to sum with the consumption of households to the production of firm I. So let me not go into the details. I've written down the calculations here to show you that you can, in principle, solve all the equations. What is important is that for the choice of the Cobb-Douglas production function, this strange product function, you can convince yourself that there's a well-defined equilibrium solution where all markets clear and everything, independently of the choice of the J matrix, of the network, input-output network, and for any choice of productivities provided is positive. So what does it mean that it's a well-defined solution? It means that the prices and the productions of all firms are all non-negative. Actually, they're all positive in this case. So you produce a positive quantity that you sell at a positive prices, which is, the least one could hope for if you have equilibrium in a meaningful sense. So how do you describe fluctuations in such an equilibrium situation? Well, economists think of the world as a succession of equilibrium states. So the economy reaches equilibrium pretty quickly. So you can compute a level of production and prices. Then there's a shock. And then immediately the equilibrium is reached again, and you can recompute the new state of the system with the ZIs, which carry the shocks, at their new values, and you carry on. So, as I said, it's a succession of different equilibria, each equilibrium corresponding to a different vector of shocks of production, of productivity Z, okay? And so what you find is that the global variance of the GDP in this economy, of the total production, if you want, is equal to what is called in some fields the Hafindel index, in other fields the participation ratio, Hafindel index of the sales of firms. So what is this? The sales is the product of YI times PI, is the production times the price. And the Hafindel index is 1 over n squared, the sum from I equal 1 to n, so the sum over all firms of the sales squared. And this is a measure of concentration of sales. So if you assume that the distribution of sales of firm sizes measured as sales is a power law with exponent mu, which is actually the case for US firms in particular. So this is actual data, and you see the histogram of firm sizes. So the frequency of a firm of a given size is a function of the size in log. So the nice slope here is mu equal 1, which is a Zipf law. Then depending on the value of mu, you find that H is 1 over n for mu greater than 2. That is, if the distribution of firm sizes has a mean and a variance. This is the standard case, if you want. It's an anomalous power of mu for mu between 1 and 2, and it doesn't scale with n if mu is less than 1. So you see that this GDP of the variance, its decays is 1 over n in the standard case where firms have roughly all the same size. That is, if mu is greater than 2, it means that the tail of the distribution falls off quickly enough for the variance and the mean to exist. And so if the variance is 1 over n, the standard deviation is 1 over square root of n. And this is the argument I was giving you in a hand-waving way at the beginning of the introduction here. So this is where this 1 over square root of n comes from. But now Gabex says, well, but you see, the firms are actually not at all narrowly distributed around the average size. It has a fat tail. And so if mu is strictly less than 1, if mu is equal to 1, there are log corrections. But anyway, if mu is close to 1 or below 1, then h doesn't depend on n. So even if the economy is very large, h can still be substantial because there's a lack of diversification of the economy. So this is really Gabek's scenario. So in the context of this firm network, you have to construct a network that generates a distribution of sizes in the economy that's parallel. So you have a network, and the network was initially constructed on the basis of trying to model correlations and model waves of bankruptcies and so on, avalanches, contagion. But actually, in the end, this equilibrium model, it boils down to the granular scenario. And you need to invoke the fact that the network is scale-free enough, is that there are hubs that are strong enough. They exist, these hubs, of course, but the whole fluctuations, the nature of the fluctuations should really be related to the nature of the input-output network. And if you look empirically, it's true that the network is a broad distribution of degrees, but it's not broad enough to explain what one would need to get the Gabek's granularity scenario. And plus, again, as I said, in this model, there's no notion of contagion or avalanches. So, as I said, this model is still very much looked and studied since Acemoglu and Carvalho revived it in 2011. There are various extensions of these models, and these models have been used recently, for example, to explain what would happen if Europe would cut the Russian gas after the invasion of Ukraine. So these models are really taken very seriously. So now let's look at what happens if we relax the assumption that the production function is so-called Cobb-Douglas. So this is a more general family of production functions that economists study as well, which is called the constant elasticity of substitution, CES, production function family. And it can be written in that way. So yi is again the production of firm I, zi is again the productivity factor. And then instead of having a product, it's now the sum over j, where I've included labor as j equals 0. So labor is one input good among others, if you want to think of it that way, of some coefficients, jij's and gij. The sum of these ratios to the power 1 over q, the whole sum to the power minus q. So it's a way to write in a condensed fashion the family that contains many production functions. In particular, if you take now the limit q going to infinity, you recover Cobb-Douglas. But if you take the limit q going to 0, then you get a production function that maybe is more easy to swallow. And it's called the Leontief production function, where now the production of firm I is actually limited by the product that's the scarcest in the inventory. So you take the min over input products of qij over jij. Jij's are kind of stoichiometric coefficients, if you want. And this is going to be the limiting factor for production. So for example, if you want to build a car, you need 4 wheels and 1 windscreen. If you have 3 wheels, you cannot even produce a single car. So that would be kind of a way to visualize these stoichiometric coefficients. Okay, so this, I think, makes a lot of sense. And you can interpolate between the two. The case Q going to 0 is a case that is strictly non-substitutable in the sense that, as I said, if you miss one ingredient, you're stuck. And on the other hand, in Q going to infinity, then if you miss a little bit of 1J, you can always compensate by buying more of another good. So you have a lot of substitution in Cobb-Douglas economies. So what you find is that if you redo the whole economic equilibrium analysis that I've laid out for you, which is households optimize, firms optimize, and markets clear, you get equations, but in general, and I'm going to be more specific in the Leontief case, in general, you don't get prices and productions that are always positive. You find that some prices are negative, which means that it cannot be interpreted as a feasible equilibrium, as a legit equilibrium. So let's look at what happens in the Leontief case. But what we find is that the conclusions are going to hold for any value of Q except Q going to infinity. So the Cobb-Douglas case is a special case where equilibrium is always feasible, but as soon as Q is not infinity, you get into problems. That is the possibility that equilibrium doesn't make sense. So Q equals 0 is not a special case, actually. The special case is Q equal infinity, is the Cobb-Douglas case. So in the Leontief limit, as I said, it's generic for all Q strictly, finite. Then in the Leontief limit, you get linear equations, and the solution of these linear equations must be non-negative in order to have something that kind of makes sense. And so these equations look like this. So Z is the vector of productivity factors, which you align along the diagonal. I is the identity matrix, minus a matrix of these stoichiometric coefficients that appear here, okay, that describe how much J you need to produce one car, say. Applied to the vector of prices must be equal to a positive vector. Positive vector means that all entries are positive numbers. And a similar equation for productions. Set I minus transpose of G applied to a vector that's related to production equals a positive vector. So the condition under which these linear equations have positive solutions is simple in the case where matrices have this shape. So it's, strictly speaking, the solution of these equations is very simple. It's P equals this matrix to the power -1 applied to K. But of course, it's not because a matrix is positive, for example, that its inverse is positive. So it may be that you get negative prices. And the condition under which you don't get positive prices is that the real part of the eigenvalues of this matrix are all positive or 0. Okay. So M matrix, this is a criterion you can look on the internet. M matrices, there are various equivalent characterization of this condition, that the inverse applied to a positive vector is a positive vector. And one of them is, which I find convenient, is related to the real part of the eigenvalues of these matrices. And M matrices are such that diagonal elements are positive and all off-diagonal elements are negative, which is the case of this matrix. What is interesting is that this type of equation arises in different situations, and one of them is the Lotka-Volterra, the multidimensional Lotka-Volterra ecological equilibria. So let me give a short digression on this. So the Lotka-Volterra, you probably all know about rabbits and foxes, but you can generalize these equations, these two-body equations in the case of rabbit and foxes, to the case of n species interacting. So dni dt is proportional to ni. Ni is the number of individual in species I. Then there's a fitness, positive fitness, that describes how adapted the species is to its environment. There's a crowding term due to self-interaction, if you want, minus Zi Ni. And then there's a term coming from interactions with others, some being competitive, that is detrimental to species I, and others being cooperative, that is beneficial to species I. Okay, so this is the standard Lotka-Volterra equation. And if you look for solutions, for equilibrium solutions, then dni dt should be 0. And if dni dt is 0, then either ni is 0, but it means that the species is extinct, or that this term is 0. And you see that this term 0 means that there's an equation of that shape. Of course, I've adapted notation such that it matches my previous notations. Zi minus g applied to a positive vector, n must be positive because negative number of individuals doesn't make sense, of course, equal to a positive vector, which is a vector of fitnesses. So you see that exactly the same question arises in the context of ecological equilibrium, except that in the Lotka-Volterra case, this matrix G doesn't need to be positive. In the case of the Leontief production factor, of course, again, it doesn't make sense to take a G negative. But in the case of species, some species can interact positively and others can interact negatively. So there can be competition, cooperation, or predator, and so on. But so what you find is that somewhat generically, if you want to have a solution to a stationary solution to these equations, then some species must go extinct. And this is really the whole argument of Robert May, will a complex system be stable, is that the stability of such equilibria requires the number of species not to be too large. And if they are too large, I mean, this is not written by Robert May, but it came later in the study of these type of equations, in particular by Piroli, Bunin, and Camarata, that actually the size of the ecology must shrink until, that is, some NIs have to go to 0 in such a way that the remaining equation here makes sense with n a positive vector. That is, if you solve this equation by writing n is this matrix inverse applied to f, then you still get the positive vector. So it's interesting to see this analogy between firm networks and ecologies, I think. So the fact that the spectrum of this matrix M has to be on the positive side of the complex plane is the so-called Hawkins-Simon condition. And let me just give you a simple case where the input-output network, supplier-client network, is a random regular network. So each firm has exactly C clients and C suppliers. They're both randomly chosen among a very large number of possible firms, and which means that either Jij is 0 if firms are not connected by a client-supplier relationship, or Jij is equal to a non-zero value, which we take to be the same for all present links. And we also imagine that all productivities are equal to some Z. So in this case, the only randomness comes from the network, which is random. But we know how to compute the spectrum of these matrices. And what one finds is that there's an outlier eigenvalue, lambda min, which is the one that has the smallest real part. And it's given by, it's actually real. It's given by Z minus CG. And then there's a disk of eigenvalues inside a circle of radius G square root of C. And that's what you see represented here graphically. It's for minus M. So the isolated eigenvalue is here, and all the others are there. So the instability really comes from this one. This is the one that can go to 0 first. And so what one sees is that the economy becomes unstable when productivity is not large enough for the whole network to sustain itself, if you want. So if C is large, Z, the productivity. So if the number of input products is large, the number of productivity must be large enough. Otherwise, there's no equilibrium. So the economy becomes unstable if productivity is too small, if connectivity, that is number of products that you need, is too high, or if the amount of goods you need to produce one good is too high. Of course, this is much too simple an example, and you can add disorder, you can add fluctuations in the productivities, you can add fluctuations in the Gs and so on. But essentially, what you find is that indeed there is a scenario by which, as the economy grows, the system is going to approach this critical point. You can show exactly like in May's paper that as the number of firms grows, the largest eigenvalue is going to shift towards everything else being the same. The smallest eigenvalue is going to shift towards zero. So at one point, a large economy will become unstable. You can also argue that because products are becoming more and more complicated, the number of inputs for an iPhone, I don't remember, I think it's 300 different products needed or even more. So this means that the little c that I talked about here is growing as the economy becomes more complex. And so again, this pushes the economy towards the critical point. You can also show that if goods are less substitutable or less redundant, this corresponds to a smaller value of Q. You remember the Q comes from the CES production function. Q equals 0 is strict non-substitutability, Leontief, and Q goes to infinity means that products are substitutable, and in this case, you don't get an instability. You don't get this problem because there's always a well-defined solution to the equations. So again, you can argue that firms that they tend to have lean supply chains because maintaining a client-supplier relationship is costly. So we're back to this idea of optimizing a system drives it to instability. And something I haven't talked about that you can include in the equations is that as firms apply what's called a markup, that is, they compute the equilibrium price, but then they increase the price to some value to get extra margin, extra profits. Then as firms seek to increase their margin, exactly the same thing happens. You push the system towards zero for its eigenvalue with the smallest real part. So all these phenomena, economy growing, network connectivity increasing, goods becoming less and less substitutable, and firms seeking to increase their margin, they all seem pretty plausible. And so it is plausible that left alone on their own devices, economies spontaneously approach this critical point that I've talked about. And of course, this was not the model that Perbach had proposed at the time. The model of this paper, you see the title, Aggregate Fluctuations from Independent Sectoral Shocks. So this is the same problem. You have independent sectoral shocks, but still aggregate fluctuations that are large. And the idea was to invoke this self-organized criticality phenomenon. But unfortunately, I think that this paper, which is really great in terms of its ideas, hasn't made it at all in the economics profession because the model that was proposed was really a kind of blunt transcription of Sandpi's model into an economic framework. And it didn't have the flesh needed to convince economists that this could be a bona fide model for economic fluctuations. But I think this model here, this Long-Plosser model with a non-Cobb-Douglas production function, really reveals something similar in flavor to the self-organized criticality scenario of Bach et al. So it is plausible that the large fluctuations that we observe in economic systems comes from the proximity of an unstable point. Because as we know, and that can be proven within this context, is that the proximity of an unstable point is amplifying any fluctuation because of that proximity. So that's one possible scenario. But let me turn to another one that is actually something that one has to think immediately after having told you the story that I just told you is, well, okay, but in all these calculations, we always postulate that the economy is close to equilibrium in the sense of economies, that is, markets clear and firms optimize and so on. But this is what would be called in physics an adiabatic limit. That is, that the system, the external perturbation to the system, change slowly enough for the equilibrium to be always reached. But there's a natural question or a legitimate question, which is, okay, good, but how fast is the equilibrium reached? And is this time scale small enough so that we can forget about the change of fundamentals, quote unquote, that is, productivity, network. Network is, of course, time dependent and so on. And maybe it doesn't make sense to make this assumption that equilibrium is reached because it takes time to reach. And actually, what we'll find is that in some cases, it's never reached. So let's go into this. So the question is, how fast do imbalances supply-demand? So supply-demand is zero. I mean, the imbalance between supply and demand is zero in equilibrium. But if it's non-zero for any reason, how fast does it go to zero? So how fast do imbalances wash away? And so what we've done in this paper with Théo Dessertaine and collaborators is to do what physicists like to do, that is a kind of phenomenological approach to the evolution of prices and production given imbalances. So what we explain in this paper is that you cannot be too naive either, because if you're naive in the way you write these phenomenological equations, then you violate some obvious causality criteria, for example, constraints. So you should be doing things that make sense. That is, consumption can only occur after production, for example. And so it's not completely trivial to write equations, even at the phenomenological level, that are actually not violating trivial physical constraints. So that's what we've done in the paper. And what we find is that there's a phase diagram in the plane of parameters that you have to introduce to give some meaningful dynamics to the model. So this is still the Long-Plosser model, even with the Cobb-Douglas production function, actually, but with some naive, quote-unquote, dynamics that is imposed to the structure of the model instead of invoking equilibrium. So there are various parameters, but essentially two very important ones are, on the x-axis, the strength of restoring forces. What I mean by this is, okay, imagine a firm observes that it overproduced compared to demand. Then it's going to be tempted to reduce production at the next time step and also reduce prices to get more demand and reach market clearing. So in front of this imbalance term, there's a coefficient telling you how fast are you going to try to correct for these imbalances. So that's what I'm calling the strength of restoring forces. This is the x-axis. And the y-axis is perishability. That is, okay, now the problem that, of course, is the reason why economists don't really want to enter that jungle is that it becomes much more complicated. Because if demand is not equal to supply at each time step, that is, if markets don't clear, then there are inventories, right? And in general, it's not unexpected that firms will overproduce, and then it has to decide what to do with the stock. And so you can be in a phase where perishability is zero, that is, it can store what it produced and set it maybe next time round, or perishability is immediate, like strawberries, I don't know, and then you don't have to care too much about inventories. And so in this phase diagram, there's a large region here, the blue region, which is what economists talk about in a way. That is, it's a region where there is an equilibrium. In the Cobb-Douglas case, there's always an equilibrium, a static equilibrium, and dynamics reaches equilibrium after a while. That's what you see in the little inset here. So probably prices, I don't remember, but there's a disturbance of prices, and then very quickly it reaches equilibrium. Okay, so in this case, you can maybe argue that it's okay to invoke equilibrium that evolves slowly. But as you increase the strength of restoring forces, that is, in a way, if firms tend to overreact to imbalances, or if you reduce perishability, then you enter a yellow phase, which is where anything can happen in a way. I mean, it can be cycles like this, synchronized cycles, desynchronized cycles, chaos. You can even have in this boundary region very strange phenomenon like, you think the system is in equilibrium, and then there's a completely endogenous spike of inflation or underproduction or unemployment, if you want. So you can have these very strange things. And by the way, for theories, what's interesting is that if you look at the equations that we've written down, and if you think about the problem, then even close to equilibrium, there's no true linear regime. It depends on in the direction in which you perturb the system. If you perturb the system in the direction where production is greater than consumption, or in the direction where consumption is greater than production, then the coefficient of the linear matrix are not the same. So it's a nice example of a cone-wise linear dynamics for which actually very little is known. So I think that for those of you who are interested in nice mathematical problems inspired by these questions, this is a nice feature. But anyway, what happens is that, okay, there's a phase where the self-organized criticality behavior invoking the proximity to an instability point makes sense within the context of equilibrium economics. But there's a huge region here where it just doesn't make sense. And in this case, you have, the system, although equilibrium is there somewhere, dynamics is unable to reach it ever. It's always going to fluctuate without any exogenous shocks. I mean, all the dynamics here is purely endogenous. And it's due to a lack of synchronization or a lack of coordination between firms. Firms overreact, and then it sends signals to other firms that are unable to correct correctly, to go in the right direction. And so it creates all sorts of desynchronized problems to the whole economy. Of course, this type of dynamics is known in other similar systems like neurons or ecologies. So this is another possible scenario for solving the small shock large business cycle paradox. Maybe we're just completely out of equilibrium all the time, and we're confronted to a completely different paradigm where it's not economic equilibrium that we need to understand, but it's really this whole non-equilibrium phenomenon that needs to be put to the front of the agenda of research. So that's what I've called spontaneous turbulence. So let me skip the last slide because, just one word is that this is also within a fixed network. I mean, the network is not changing, but of course the network is also changing. So it adds another layer of complexity. And we've done some work with Céline Collomb about this, if you're interested. So in conclusion, let me quote Olivier Blanchard, who was head economist at the IMF when he wrote this piece, reflecting on the 2008 crisis. So the piece is very nice to read, Where Danger Lurks, from 2014. It's easily accessible on the web. We in the field that think of the economy as roughly linear, constantly subject to different shocks, constantly fluctuating, but naturally returning to equilibrium over time. So you see, I'm not inventing. It's exactly how they think about the world. And so this is a marble in a bowl. So the bowl wants to go down the marble wants to go down in the bowl, but the bowl is shaken because of exogenous shocks. The main lesson of the crisis, i.e. the 2008 crisis, is that we were much closer to dark corners, that's his way of describing it, situations in which the economy could badly malfunction than we thought. Okay, so I think this is really what I'm trying to illustrate here. So the firm network scenario for small shock, large business cycle, as I said, either the firm networks become unstable in a whole swath of parameters and the system stops short of being unstable, but then fluctuations are enhanced. This is the self-organized critical scenario. Or we have to embrace the fact that there's nonlinear dynamics coming up as soon as you try to endow the system with some kind of reasonable dynamics. And then the system is generically unable to reach an equilibrium that exists, but is out of reach because of the dynamics that's overreacting in some region of the phase space. So that's essentially what I wanted to convey, and I think I should stop here. Thank you.
Thank you very much, Jean-Philippe. And we have now time for questions. I don't see that. Yeah, please, Jurko.
Thank you very much for this two very interesting lectures. I have the question with respect to the second part. In fact, when you mentioned Lotka-Volterra model, also it was a pleasure for us living in Lviv because Lotka was born in this city. He was born in Lviv.
Okay.
Yeah. So my question is, when you mentioned this work and the model of Acemoglu and Canvargo, and you were speaking about network structure, how does it impact the overall behavior? You mentioned that for small values of mu, you have different regimes. And especially when mu is smaller than 2 and mu is smaller than 1. Then
yes.
I have two questions. First is that for these low values of mu, when mu is smaller than 2, even the mean node degree doesn't exist, right? And
No. Less than 2, the mean exists, but the variance doesn't exist.
Well,
it's when mu is less than 1, then the mean does not exist.
Yeah, exactly. Yeah, when mu is less than 1. And it means also that when mu3 is not typical, is not marginal value for your case. In critical phenomena, mu3 is marginal because it reflects the susceptibility, so to say. So does it mean that in these processes, the quantities which are related to susceptibility are not that impactful on the overall behavior?
Yeah, I think that here you're really computing a different object, and the size distribution is related to the degree distribution kind of trivially, and so you're blind to susceptibility in that sense. But remember that these models there's no dynamics in these versions of the model. So I guess that, yeah, if you endow, as I was trying to do this in the second part, if you endow the system with some dynamics, maybe mu equal 3 will show up. I don't know.
Okay, thank you.
But by the way, what I've shown, the phase diagram I've shown is actually not even for a scale-free network. It's for a random regular graph with no fluctuations of connectivity. So these generic oscillations, they are not due to strange distribution of degrees.
Right, thank you.
May I ask you a question, Jean-Philippe?
Of course, yeah.
you gave a list of possible explanations for the problem, for solving the problem of this discrepancy between the observations and the expectations, so to speak. And you mentioned that this broad distribution of the company sizes and the network inhomogeneities and non-equilibrium properties and so on. I have a trivial question. Couldn't it be that all of them play a role? In a sense that I just want to mention that we, with people from the Complexity Science Hub, Stefan Turner, and others, did some calculations for a country's firm level input-output data, and introduced a quantity called economic systemic risk index, which is observed by playing, so to speak, the game with the data and then removing one company and looking at the impact of this event. And what came out was that this economic risk index is extremely homogeneous, and there are very few companies which have a very large impact. And more interestingly, these are not only or not necessarily the biggest companies. So there are also some small companies which have large impact. So I just want to say that.
No, I think you're absolutely right. I mean, my talk is not saying that I've solved the problem. Far from that. I'm just trying to say, and I think this is very much a physicist approach, to say, okay, well, let's see what a model says, and then try to go to data and see which mechanism is dominant. Whereas economists, in a sense, they're not interested in the scenarios that are generated by a model. They want a model, and then they want to fit the model to data. And if you don't do that, then you're accused of being, doing things that are irrelevant. But I think it's, I was really interested recently by a talk on a completely different subject by Subir Sachdev on ITC superconductivity, where these people, they've been working on scenarios that were proposed by Phil Anderson in the 80s, and they were really scenarios, and it took 15 or 20 years to go, or maybe even more, to go through these scenarios and to see what these scenarios are really predicting, and then go back to experiment. I think it's important to keep in mind that there is an experimental question you want to answer and not go completely in the wild, but it's also important to leave people propose scenarios and see which ones, and sometimes scenarios are pretty unexpected, and these unexpected scenarios, sometimes they're really useful to understand realities. But I think that it's important to explore these scenarios. So what I've shown today is just a list of scenarios. And actually, when we started this study that I've talked about, we were really happy with the self-organized criticality scenario, and we thought, great, this is what Bach and Al had in mind, and we now have a nice incarnation of their scenario. And then we tried to put dynamics, and then something completely different came out from this dynamic extension, which is that you don't even need instability and self-organized criticality, that you can just have, as I said, a random regular graph that's, from an equilibrium point of view, perfectly stable, but its dynamics is going to do all sorts of things that may be relevant to economics. So in answer to your question, I think that there are different mechanisms, and the real experimental question is to know which one is dominant. And I'm very open to any answer to that, because I don't know.
Yeah. I absolutely agree. And this scenario with approaching a threshold or a limit where the system becomes unstable is certainly appealing. if I may, I have another question which is related to that. You have shown that in the first part of your talk that if you drive the parameter j large enough, then suddenly a first order transition happens with a jump. And at the same time, you also emphasize that this is a kind of critical point where the fluctuations may grow enormously. However, in a first order transition, they don't grow necessarily too large.
No. I mean, I think that, okay, yes. No, the critical point is JC, but the discontinuity is a spinodal point. It's when you drive P at a fixed J greater than JC. So you're not critical anymore. So there's no criticality at all. There's no precursor, there's nothing. And you just have a jump, but you're far from JC. JC is the critical point.
Yeah. So this is a spinodal. That is.
Yes.
Then I understand. Okay. Thank you.
We have one more question from MFAM. So please.
Thank you for your talk. I just have a question about the last part of your second talk, like about the fact that the network structure, the connectivities, and maybe the heterogeneity in the couplings constant Jij can also change. But you stress the importance of the difference in the time scale between how this network structure changes and how the as a quantity like the G or the Y, the production changes, right? The price changes. But could you elaborate more on how the network structure changes? What is the dynamic? Is this like become more heterogeneous over time, or is less heterogeneous over time?
Yeah, there are two ways the network can change. One is because of technologies, as I said. I think that if you take long time scales, then products now have input goods that are in much larger quantities and coming from many parts of the world. Again, if you think about the iPhone, than what we observed in the past. So I think there's an argument to be made about the fact that networks are on average getting more and more connected. But on the other hand, there's another way networks can change, which is not taken into account in everything I've said, which is that in general, each firm has the choice between different suppliers. And so here we assume that the set of suppliers of a firm is given, but in reality, there's a set of suppliers from which each firm can choose, and in principle, each firm has to choose suppliers that reduces the cost of goods as much as possible. So you can add this other layer of dynamics where at each time step, each firm looks in the set of suppliers that matches technology. Of course, if you're a baker, you're not going to be interested in tires, but you're going to be interested in people providing flour. So if you add this level of complexity, then you add another slow dynamics to the system. And what we find is something related to spin glass dynamics in a way. That is the rewiring of the network itself becomes a slow process, on top of which you have the things that I've talked about.
Thank you.
Well, it was a great pleasure to give these lectures, and I hope you have 2 great days. Thank you for inviting me.
Thank you very much for coming to Lviv virtually, and we hope in Lviv and Ukraine that at some peaceful right day.
I very much hope to.
Thank you so much.
Goodbye. Bye.